Syzygy, episode 87, Star Go Boom. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, here in the office of the fabulous Dr. Emily Brunsden here at the University of York. Hi, Emily. How you doing?
Hello. I'm very well, thank you.
Excellent. Now, today we're going to be talking about something which, to me, is I find this topic today really, really exciting because it talks about something that we normally talk about a little bit. I was about to say in the abstract. That's not quite right. We normally talk about it in the past tense, right? When stars come to the end of their lives, then a number of different things that can happen. But one of the most exciting things that can happen is that they go boom, right? They explode in what's known as a supernova. But normally we talk about that in the past tense because we see what's left over. You don't often witness a star in the process of its death and going boom. But turns out just over the last year or so, we have, which is really exciting. So we're going to be talking about that today. It involves the use of a couple of our space-borne telescopy friends. I think we've got a bit of input here from Hubble and from TESS. So before we get into the story today, I just wanted to make note of, Emily, have you heard of any of the difficulties that Hubble's been having over the last little while?
I've been skipping over them in my news feed. I'm too scared to look.
You're very busy as well. There's a lot going on. Seems like Hubble's been having a bit of a data problem. And a little while ago, some of their transmissions, communications, something like that, went awry. And so the team went, right, that's it, shut it down, pull the big switch, ka-chunk. And Hubble went into safe mode for a while, which I think is fabulous. It sounds like the sort of thing that you'd do with your laptop computer. Just put it into safe mode. You can do that with an aging space telescope too, turns out. But everything seems to be okay. They've turned back the main mission camera. They turned that back on again so that they can do some real research again. And that's up as of just 2 days ago, I think. But the rest of the systems are still in safe mode. So fingers crossed for Hubble. How far are we into, Emily? How far are we into borrowed time with Hubble?
Well, ages and ages and ages.
Like the mission was supposed to have lasted for how long? And then that finished years ago, right?
Yeah, I think even a decade was pushing it by that point. So yeah, we launched, what was it, the early 90s. We got our sort of first great images about 1995. So she's getting on a bit. We've had our 30th anniversary.
Doing well. So I think every once in a while, having Hubble say, I'm just going to have a little rest for a bit. Like just stop it with your communications. Just shut up for a minute. I'm just going to have a little rest. Fine. I think that's okay. Who wouldn't? I mean, the Queen did. The Queen got to have a little rest and not do some of her queeny things for a while. I think Hubble gets the same kind of benefit, don't you?
Yeah, I think fair. Hubble might be a similar age to the Queen if you compare the years sort of equivalently.
Is that a bit like dog years? You've got dog years and Hubble years and Queen years. And Queen years, like the Queen's going to go forever. So who knows? Anyway, Hubble still going. And point of Hubble is in today's episode. Hubble has spotted something really interesting in the realm of supernovas. So Emily, over to you. What are we talking about today? What's been seen?
So we're quite good at picking up supernovae events because they are very, very big, bright explosions that happen when a star dies. What we're not so good at is perhaps actually seeing them kind of as they happen. So catching them in their very, very first moments as they start out. So this is exactly what that is. We have seen not only a supernova before it went kaboom, but also whilst it went kaboom and afterwards, as we normally do as well.
Has that ever happened before? Have we ever been lucky enough or clever enough to actually catch that whole process?
We have got a few. The problem is that most supernovae that we observe are actually really, really faint because they're very, very distant galaxies. This is a very nearby galaxy, so it's lovely. We can get beautiful images of the galaxy and see the brightness changes, but we can also get spectra, which tell us a lot more about the supernova event.
All right. There's so much going on here, and it's just so interesting. So why don't we just back up a little bit? Who's done this research? And I think you mentioned before we even started, like you even know one of these people. So who's the team? Who's
Astronomy
involved?
Can be a small world sometimes.
Well, yeah.
So the team, the paper's been led by. I'm sorry, I'm going to mess
Let's
up. This
mangle
person's
some names here. Right to Emily.
Samaporn Tignano. et al.
Okay.
So that's a team that's been led from the University of California, which is perhaps no surprise because, as we'll see, the main supernova kind of alert facility, which is the Zwicky Observatory, is based out of California.
I love that. I mean, imagine going to a party and say, what do you do? Well, I'm on the supernova alert facility. Really? Tell me about that. You'd be just having free drinks all night, I reckon.
Yeah, and so they led the team. It just so happened that the second author on the same paper was somebody that I did part of my postgraduate work when they were an undergraduate. And
Which either means you're really, really cool and well-connected, or, as you say, astronomy is very, very small area, or both. It could be both. Why can't it be both?
So what we've got here is a very, very exciting in the terms that the supernova that was found is very close. Now, if we start from maybe that point, that's a good
Okay. All right.
thing to
Close in
start.
astronomical terms.
Yeah.
How close?
Well, and we're talking about 60 million light years.
60 million light years. Okay, now we do this regularly, so I'm starting to get a feel for this. My inevitable point of comparison is the next big galaxy that I can think of out there, which is Andromeda. That's like 2.5 million light years away, and so this is 60 million light years away.
Yeah.
So that is quite close on a cosmic scale.
Absolutely. It's close enough to have gorgeous Hubble images.
Right.
My computer screen just got flashed off, but it did have a picture of the lovely two galaxies.
Well, look down at your podcast player of choice now. If you have chapter art, it'll be showing right now. So have a look.
Yeah, so there's two galaxies here, two big spiral galaxies. They're actually called the butterfly galaxies, which is rather
very
nice.
pretty.
Interacting galaxies, but it's in one of these galaxies known as NGC 4568 that we have had supernova 2020 FQV go off.
I liked butterfly. I think we should have stuck with that one. But okay, so we've seen the supernova, and you mentioned before, we see supernovas, like we spot them. They're often very, very dim, but this one's special because it's in a galaxy which is pretty close. That helps.
It absolutely helps. It means we can do much more follow-up work on it using not only the space-based telescopes that we're talking about, but the ground-based telescopes that allow us to do the spectroscopy, the color photometry, all the kind of stuff to really dig into some of the interesting parts of supernova. And as, even people that I've worked with, I did a little kind of sojourn into supernova research many years ago. But there is a kind of a thing in the supernova community that many people talk about is that you're often doing kind of what they call crime scene investigation.
Right.
So what that means
Forensic
is
supernova research.
You're trying to figure out things that happened or what was the star like by looking at the remnant of the supernova that's been left behind.
Right. You've gone into the room where there are, forgive the graphic nature of the description, there are the blood stains on the walls, the furniture's been overturned, and you've got an empty shell casing over in the corner, and you have to reconstruct the crime. You're doing the same from what happened here. We can see this supernova remnant. Let's model that backwards in time. What did we have to begin with?
Exactly.
Is that an easy thing to do?
Well, it's a really interesting thing to do. I think we have some good techniques, but there's always a lot of uncertainty because, you're undoing one of the biggest explosions that we have inside a galaxy.
Yeah.
Right?
I mean, these are big, aren't they? Can we just for a moment, just pause for a second to say, how big is a supernova in terms of explosions? Like how bright are these things?
Well, you know where I'm going to go here, right?
Oh, you're not going to, yeah.
We've got a stat attack for you.
Oh, no.
It's
Okay. All right. Stat attack time. Hit me with it. Stat attack, which is where Emily tests Chris on his very rudimentary knowledge of all things astronomical. Go for it.
Right. How bright is... I'm going to give you supernova. I mean, there are different types, and we'll mention that, but let's go with this one.
Sure.
How bright is a supernova?
Do I get a scale or some kind of comparison? You're going to give me
Compare it
any...
to the sun? That might be useful.
Brighter than the sun.
Absolutely. Well done.
Brighter than a lot of suns. I'm going to just drag something out of the back of my brain, which is that a supernova can outshine the entirety of a galaxy.
Can.
Awesome. Good.
Small
I'm going to go with that.
galaxies?
Yes, small galaxy.
Right.
Very small galaxy, very big supernova.
Yep. About a billion times the brightness of the sun.
Wow. Okay. And given that our Milky Way has got, what do we got? About a couple of 100 billion stars in it?
Yeah.
Okay. But that's still really bright.
We're a big
right?
galaxy.
That's stupidly bright. Okay. Big explosion. Boom. Yep.
Here's a good one. How often there's two quick parts here. How often do supernova occur and how often do we see them?
Right.
You can pick
okay.
either one or both.
How often do they occur? Well, again, this is a relative question because in a potentially infinitely large universe, they're happening constantly. So I would say within the galaxy, 100 billion. I've got nothing. I'm going to say in our galaxy, once a day.
I think we might be in trouble if that were the case.
I have no idea. How often do
In
they
our
happen?
galaxy, we're looking about once every 50 years.
50 years. Right.
Yeah.
So I was only off by several orders of magnitude. I mean, I've got nothing. I've got nothing to attach that to. 50 years. That's a lot longer than I would have thought. Like, I would have thought in our galaxy, with the number of stars that we've got, even though we don't see them, we wouldn't see them because there's a lot of stuff in our galaxy and there's a lot of stuff between us and the majority of the galaxy. So we just wouldn't spot them all the time. But once every 50 years, that's not a lot.
Well, if one did go off in our galaxy, you'd know about it, right?
Right. Well, even on the other side, though?
Probably.
Wow.
Well, because you still get enormous things like neutrino fluxes and so on that
Okay.
would come through.
So question, if it's once every 50 years on average in our galaxy, that implies that within the last century, we probably would have seen one. So
Probably,
Have
probably.
we seen one in our galaxy?
Almost.
Almost.
Almost. The closest we've come is supernova 1987A.
Ah, that was in our galaxy.
Well, ish.
Ish.
It was in the Magellanic Clouds.
Right, which is just next door in the
Yeah,
backyard.
very close, very easily observable.
Mm-hmm.
And it's actually still on the whiteboard to come back to that supernova because it's an interesting one.
It
in
is,
its own
actually.
Right.
It's down the bottom of the list, yeah.
Yeah. But yeah, so it wasn't quite our galaxy. It's one of our little dwarf satellite friends.
Yeah. So far enough away to not be life-threatening, but
Well, exactly.
wow.
But still, pretty impressive.
Yeah, I'm suddenly a little bit nervous about that, but that's a topic for another time. Let's push that aside. Okay, once every 50 years for a supernova. How often do we see them? Well, if you count all the different places that we could see them, which is not just in our galaxy, but potentially in other galaxies as well, I don't know. Once a year? I don't know. How often do we see a supernova? Oh, look, okay, hang on. If there's an entire team dedicated to supernova alerts, then it must be reasonably often enough that those people aren't sitting around being bored for the majority of their lives. So I'm going to say a couple of times a year.
So even I was pretty shocked when I delved in and found out these numbers. So I sort of thought that we were kind of in the hundreds-ish per year. That was where I sort of... And the way that I kind of knew roughly that might be the case is actually because of the way that we name supernova.
Named by year and then by letter?
By, a string of letters, and
Yeah.
you can decode those letters. I'm going to tell you all the gory details about that because I found out about it, exactly how to do that, and it's really exciting.
And if you had to go through the pain of finding that out, then you're going to share it with us.
It's fun.
Okay.
I like it. But anyway, so the fact that you've got several letters, you get supernova, blah, 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 IG, whatever, there's, that there's going to be a few
Yeah.
around.
Although 1987A, well, that's just A. Is that because we weren't seeing many in 1987 or?
It was the first one to be seen in 1987.
Right. Okay. So fair enough.
But yeah, no, what's interesting is in 2020, we spotted 19,242 supernova.
That's a lot of stars going boom. That's a lot more than I could possibly have imagined. Like that's many, 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 many a day.
Exactly, yeah. And remember, the majority of these are really, really faint objects that are happening in kind of big, grand surveys of the universe. We've got lots of all-sky surveys that run both from the ground and from space. They pop up kind of relatively, clearly, really regularly.
Yeah.
But for the vast majority of them, they're just so faint we don't get a lot of information about them.
And are these actual, like, you're spotting the star going there on the, in the image, or is it we've spotted a remnant? And so we count that as,
It's generally you can see the bright
You
pop.
can see that, like,
but
the flash.
You don't necessarily get it as it's happening, of course.
Sure. But you can see, like, it's not, hey, we looked over here and we found an old remnant that must have been a supernova like 100 years ago or something like that. It's not that. It's that thing went boom.
Yeah, a few days ago,
That's
probably.
extraordinary. Okay, so that's a lot.
Amazing,
right?
yeah. And interestingly, 2021 already, what are we today? November something.
So most of the year,
Yeah, we're already up to 19,174.
Wow.
So we're going to beat last
Come
year's
on,
record.
2021.
Yeah.
People say that 2021's been a rubbish year. Well, it hasn't been for supernovas, unless you're quite close to it, in which case it would have been a very rubbish year.
Well, let's hope that still doesn't happen. My final stat attack, this is going to come. And if you really want, I'll give you some license to respond in your units of choice.
like I have a choice. But anyway, okay.
How much energy is released in a supernova explosion?
Lots and lots. More than would be healthy. More than the recommended daily allowance. I have no idea, Emily. I've literally got no base level to go off there. I'm just going to have to pass. I've got nothing.
Well, you can actually break it down into sort of a couple of interesting different ways.
You
can look at the brightness and you can say, well, these things, they flare up in brightness, then they stay sort of bright for a few days to maybe a couple of months. Therefore, in most of these type 2 supernovas that we're talking about, you're looking at something like 10 to the 42 joules are released in its bright period.
Look, it doesn't matter what units you're talking about. 10 to the 42 is an extraordinarily large number. That's a 1 followed by 42 zeros, Emily, just in case you weren't aware.
But a joule's quite small.
Yeah, well, it is. But, I mean, we measure, food calorific value, food energy in terms of, kilojoules in the tens or hundreds or thousands a day. And this is 10 to the 42 joules, which is a lot more than that.
Now, I didn't calculate how many Kit Kats you would have to
That's a lot of Kit Kats
to be a supernova. But I did calculate
Kit Kat the size of the galaxy.
Let's go for the sun. The sun has an energy output. I think I even have it on my board yet. 4 times 10 to the 26 joules per second, which means that...
Which is, okay, that's a lot.
Yeah.
Like 4 times, 10 to the 26 is itself an enormous amount of energy per second. So, okay, this can't be that much more than that, but turns out it is.
Yeah, so you'd need to take the entire energy output of the sun and wait 79 million years to get to the amount of energy that the supernova puts out.
All right, so if anyone was in any doubt about how scarily dangerous a supernova is to be standing next to when it goes off, then that should do it for you. That's a lot of energy.
And that's just the brightness increase. Because it turns out, although you get 10 to the 42 joules in the brightness change.
So in terms of brightness, you're talking sort of electromagnetic energy. That's the light coming off in all sorts of different wavelengths, but that's light.
Yep.
Yeah.
The total energy is probably at least 100 times that.
And okay, so if it's not electromagnetic energy, what is it? Is it neutrinos?
It is neutrinos. Yeah, exactly.
Which is staggering, given that of all of the particles which actually have mass, the neutrinos have virtually none. And so to get that amount of energy into a bunch of neutrinos is no small feat.
That's a lot of neutrinos.
That's a lot of neutrinos. And if you, we've got countless millions of neutrinos passing through us every podcast that we record without even hitting us. But I'm imagining being near that kind of flux of neutrinos, you'd notice them.
Exactly.
Yeah.
And that's why even if a supernova goes off on the other side of the galaxy and we just can't see it because of all the gas and dust and stars and etc. that are in the way, we are going to know from the neutrinos.
Right. Would that be, if a supernova went off on the other side of the galaxy, would that be dangerous to us? No. But we'd see it.
Neutrinos themselves aren't dangerous until you get to basically standing next to the supernova. In which case you've probably got other problems.
Yeah. The neutrinos are kind of secondary on that point. Yeah. So summing up, then, it's a big boom. It's a big bang.
Exactly.
Cool.
Yep.
Okay.
Now, I've been sort of alluding to these stats in terms of they are come from type 2 supernovae.
Which implies that there is another type.
There is.
Yeah.
There's type 1. Now, we've talked about type 1a supernovae, which are probably the most famous because those are the really exciting ones that get us, the really, really bright light curves that we use to measure distances in the universe.
Right. Yes. You can use them because they happen, if I remember correctly, they happen pretty much the same way every time.
Exactly.
If you have a type 1a supernova, then that's the same as another type 1a supernova. And it looks really, really familiar. So if you see one a long way away, then you can use that to figure out how far away that thing is.
Exactly, because you know what brightness it is intrinsically.
Right.
All other supernovae, you don't have that information because they could be a small supernova or a big supernova.
Which is really
vary.
Cunning on the part of the universe to give us that, what are they called, standard candles.
Exactly.
That because it happens the same way every time, it gives us this really long range rung on the cosmic distance ladder. We can use that to measure distances out a really long way, which is handy if you're an astronomer, Very useful.
Type 1As are quite rare, though.
Right.
They definitely do not make up the majority of supernovae.
Okay.
So what we do have then, we have these two classifications, type 1A being a subclassification of type 1. Type 1 and type 2 are distinguished fairly straightforwardly by saying, do you have hydrogen in your spectrum? If the answer is no, then you're a type 1. If the answer is yes, then you're a type 2.
Okay. And is that because they come from different end points of stellar evolution? Like what differentiates, why does something have a type 1 versus a type 2?
Yeah, the main reason is because if you've got a type 2, then this is what we call a core collapse supernova. It's a really enormous giant star that's ending its life, and it will collapse in on itself. It's got no forces left basically to hold up its outer layers, so you get this enormous, first of all, infall of material, then explosion in the supernova. But because the star is just kind of like a typical red giant big star with lots of hydrogen in its atmosphere, then when the explosion happens you see hydrogen.
Right. Okay. So that's your type 2.
That's type 2.
Type 2 has hydrogen.
Yep.
Okay. And that's what we've seen with this one.
Yep.
This is a type 2.
Single star core collapse. So it's a star that's come to its end of its life. It was just a bit too big to become a white dwarf like the sun will. So a bit bigger than the sun. So it's become this core collapse supernova.
Now, Emily, earlier in the show, you said that supernovas have names, and their names are based around the year and a bunch of letters, but there's some kind of decoding that we need to do. How does it work? How does the naming work?
Well, this is, okay, I'm only going to go on about this because I found out about how to do it, and
Right,
now I
that's
feel
right.
the necessity to tell everyone else how to do it because it's very fun and exciting.
You learnt, you pass on that knowledge,
And if you're a bit of a math geek, then you'll like it.
which I am.
Yeah, so it's actually a form of kind of different change of base. So we're basically moving from a base 10 numerical system to a base 26.
Base 26, of course. Why 26?
Okay, so what that means is we've got the supernova's year, which is fairly straightforward. You can say, 1987,
That one's the
2020.
easy part.
Yeah, we can get on board
Spot
with
that one straight away.
Then it's the letters after that make it base 26.
Oh, okay, that makes sense. Yeah.
26 letters in the alphabet.
I could have guessed that. Yeah.
And so, the very first one that you start with, you call it A.
Sure.
Then B, then C,
Yeah.
etc. Except very quickly you run out of letters of the
Well,
alphabet.
with 19,000 of them, yeah.
And so then you move on to the next letter and you start calling them, say, AB, ABC, ABD, ABCD.
Well,
You
I
know,
mean,
yeah.
but you'd go through like AA and then AB and then AC and
Yeah,
then AD. Right?
exactly, yeah.
Which is the equivalent of 10, 11, 12, 13, but in a base 26 with letters. Okay, cool.
So if you want to calculate the actual number of the supernova of its
Yep.
year, because you want to know,
Why wouldn't you?
then all you need to do is take the last letter,
Mm-hmm.
figure out what number letter it is in the alphabet. So in our case, we've got FQV.
FQV, right. So take the last one.
Yeah, what's V? I had to do this on my fingers before.
Hang on. A, B, C, D, E, F, G. It's
22.
22.
Yeah, okay. So that's the 22nd letter of the alphabet, right? So you have 22 and you're going to add 22.
Mm-hmm.
Right, next one, go backwards. Q, so the
Q.
middle one.
17.
Okay, so you multiply that by 26.
17 times 26, which is a lot.
Yep. Okay, so now we've got 17 times 26 plus
Yep.
22.
Yep.
Then we go all the way to the first letter, the F, which is I can do this one, it's the 6th letter of the alphabet. Oh no, you're getting out the
Yep.
calculator.
So we're up into 464.
Because that's 6 times 26 squared.
26 times 26. Bloody hell. 4,520.
That's what I got as well.
Hey! Wow. Okay. So just in the same way that it works for base 10, except base 26, math geeks everywhere do it correctly. And what did you say it was? FQV.
Yep.
FQV is shorthand for 4,520.
Yeah.
There you go. Nice one. Now, a minute ago, before we got into the whole stat attack thing, which I failed miserably, we determined that there are a lot of these happening all the time that we spot, right? Like this year alone, over 19,000. So why are we reporting this one today? What makes this one an interesting, newsworthy supernova out of the 19,000 that we've seen this year?
Well, because there's two reasons, I think. And the reasons come down to what we've been able to observe from it. But if you dial that back to actually why we were able to observe the things that we were able to observe, that's an incredible story, I think, in itself and worth telling first.
All right, let's do that.
So this supernova was discovered in March the 31st, I think it was, 2020.
Right. So about a year and a half ago.
Yeah. So it was discovered, and it was about 18 hours post explosion. So it had exploded. It was, and what happens is you get this sort of very rapid, we call it rapid rise. It takes, a few days to get up to its peak and then drops off again. So 18 hours after the explosion, we'd noticed that there was this thing happening, this brightening of this object in this galaxy. So that was what was picked up by the Zwicky Transit Facility. And then what's sent out at that point is something very exciting, which kind of sounds old-fashioned, but it's an astronomical telegram.
Sounds very old-fashioned. Was it sort of sent by tapping the little thing? Dot dot dot. No, that's Morse code. Do they use the word stop a lot in an astronomical telegram?
Well, of course, it's all done by the internet these days.
Right.
But in the past, it would have been.
Is it delivered by horse? At least tell me it's delivered by horse.
No, not delivered by horse. But there are these alert systems around the world for different types of things that we don't know when they're going to happen, but when they happen, we're really interested and we want to study them.
And you need to move quickly.
Yes, exactly. So an astronomical telegram goes out, and that triggers, for example, a lot of ground-based observatories to start looking at this object. Because what was happening is you get these all-sky scanners, and there's several of them around the world that are just looking at the night sky all night and just looking for things that change, right? So the Zwicky telescope, for example, I think it's the Palomar Observatory, they cover the entire northern hemisphere sky in 3 nights.
Wow.
Looking for things that change.
Wow. That's fairly impressive.
Yeah, amazing. And so as soon as they spot something, they send out a trigger alert, and then any other telescope in the world that's connected to the kind of networks will say, hey, there's this new thing, let's go and look at that, as kind of a matter of urgency.
Right, because something that's able to cover the entire sky every 3 days can't be looking in huge amount of resolution and detail, I'm assuming. And so the message goes out saying, quick, look closer, just look at this bit here.
Yeah. And you want to get lots of observations of these objects because you want to look at them in different color bands, for example, if you're doing photometry, or you want to get some spectroscopy so you can figure out what the elements and so on are happening at this time. So these go out, and then lots of facilities will try and observe it. Obviously, not everyone can. But what was very exciting about this was also that they realized that, hey, guess who's already pointing at this particular piece of sky? Just doing
anyone
its
we know?
Own merry little thing. And that was Tess.
Tess, our own pet personal favorite here on the podcast. Tess, which is normally hunting for exoplanets. I mean, it's in the name.
Yeah.
So it just happened to be looking in the right direction, but it's an exoplanet hunter. Why is that useful?
Well, so Tess is really just, again, in some ways, another all-sky survey telescope. What it does is it's looking through the entire northern and southern hemisphere skies, spending about a month looking at kind of each patch of sky and just looking at the brightnesses of all the stars that it can see, and which includes galaxies, I guess, of course. And so for exoplanetary science, what you're looking for is that dimming when an exoplanet passes in front of a star. But of course, other things can happen in that patch of sky when you're observing as well.
Tess doesn't know if it's a star or a planet. It just knows that it's looking at something and that the brightness changed.
Yeah.
So that's useful.
So Tess was working in Sector 23
right.
At the time.
One of my favourite sectors.
Yeah, which was from the 18th of March moving on to about the 16th of April. So it had been observing for several days before the supernova went off.
So it was already pointed in that direction. They didn't have to sort of, Tess, turn around this way. It's like, no, we've got a thing looking right now.
Yeah.
Awesome.
Yeah, so Tess doesn't respond to these it's a survey, so
right.
It's got a predefined program of observations.
Point Tess.
No,
right.
No. Some telescopes you do, some of them have pre-programmed observing programs. But Tess just happened to be pointing at the right bit of sky.
That was lucky.
Yeah.
That was cool.
So, I mean, you can ask, why didn't Tess pick it up? Why didn't Tess say, hey, this supernova happened a few hours earlier than what was picked up by the other facilities?
Yeah.
But what was interesting, of course, is how Tess operates, is it's not designed as an alert facility.
Right. It's not looking for, hey, we found a thing, quick, everyone look at it. It's, we're gathering lots of data, now you go find it.
Yeah.
You find the thing.
And so Tess only does 2 data downloads a month.
Right. So it was pointing in the right direction. That was incredibly lucky, but it wasn't the kind of mission that was going to turn around and say, everyone, I think I just saw something. Have a look over here. that took someone else to trigger. But the fact that you've got TESS pointing in the right direction means that. So am I right in what you understanding what you're saying is after the event, the alert was triggered, but you were able to then rewind and look at the data that TESS had because it was already looking there.
Yeah, exactly.
That's so cool.
So all you had to do was wait till the end of the month, end of the sector, get the data download. Oh, hey, there you've got a new light curve of a supernova.
What are the odds of that? Like, that's crazy.
Well, for odds of such a bright supernova as well are
so
really,
close.
really small. Yeah.
Wow. Okay, so we've got and other telescopes turned and pointed in that direction?
As you mentioned, Hubble.
Yeah.
And Hubble was a really impressive one as well. So Hubble does have so the way that Hubble works is you as a scientist will submit a proposal to Hubble to say, I want to observe blah, right? And
I'm guessing most of the time the answer to that is no, get in line. There's a lot of people.
Yeah, it's it's a competitive process. Your proposal gets peer reviewed. It's actually double-blind peer review now, which is quite interesting.
That's good. Mm-hmm.
Yeah. And so what they do is they choose a number of projects that they're going to operate in a particular time frame. Now, some of those are very much kind of, hey, we want to get some pictures of this thing. It doesn't really matter when because that galaxy is not going to change over the next few.
It's not going anywhere.
But we just need some data on that galaxy.
Yep.
And some of them, sometimes they are time-sensitive observations. Like they might say, well, we need to get this exoplanet, and that's going to happen on July the 13th, and you need to be there at that time. But you also have these, what they call targets of opportunity. So you can actually submit a proposal and say, hey, if we get an alert that says something cool is happening, can you please just drop everything you're doing and go to this target?
And I'm assuming that still needs to, like, that's all got to be approved in advance. But are there many of these things where you'd be able to just say, whoa, hang on, point, Hubble, there? Like, that can't happen too often, can it?
There are quite a few different types of transients or what we call sort of, transients as in they just sort of suddenly happen. And they all have different sort of parameters of observation. Some of them really need to be done within a few hours. Some of them can, just need to be done in the next few days. It depends on the science you want to do and what the object is. I mean, other big ones are things like near-Earth asteroids. They are usually only discovered when they're quite close to the Earth.
Yeah. And that would be pretty time-sensitive.
Yep. Stars that flare is another one. Gamma-ray bursters. We want to find what does the host galaxy look like. So there's quite a few of these kind of targets of opportunity.
So presumably there's someone whose job it is to make that call. Like someone has the job of saying, yep, do it. Turn the telescope.
Yeah, well, your observing program's already pre-approved. Like the scientists have said, yes, this is a thing we want to do. If it happens, great, we'll do it. But there is a step in between, which is when you find your alert coming in, it's not just like point and shoot, Hubble. You've actually got to then do all the work behind setting up what exactly the settings are you need effectively for Hubble. How long are your exposures going to be? What cameras are you going to use? What filters are you going to... There's quite a lot, and that will change depending on how bright your object is.
Yeah, I mean,
right?
it's not a box brownie camera. This is not just turning your iPhone around and pointing at it. This is a big deal.
Yeah. And what was astounding is that whole process of just setting up a new observing sort of procedure took about 2.5 hours.
Wow.
So it was really exciting.
On the other hand, I kind of feel like that's not a lot of time.
Yeah.
Like there would have been some really busy people at that point going, go, quick.
Yeah, amazing. And all around the world, right?
Yeah.
So if you go from 18 hours post supernova, which is when we first detected it, the first ground-based observations started coming in about 26 hours post spotting it. I'm guessing they had to wait for nighttime. That's
kind of makes sense. Yeah.
Usually what you have to do on the ground. And then by the time they got the Hubble alert out to Hubble said, yeah, that's fine, we'll do it. They've set up their observing program and etc. There was only 79 hours post the supernova, which I think is a record for Hubble.
Wow. Okay. So up until that point, the only data, just piecing this together, like by the time you've spotted it, the clock starts then, and you then start trying to get as many different things pointed in that direction. But up until that point, the only thing that they've got is TESS. And so you're limited in terms of the lead up data, But then after that, you just throw as much more onto that as you can possibly get.
Exactly.
Yeah.
Yeah. So you've only got whatever you've got from the past observations to go in beforehand, but then you can try and send them as many alerts. And so this is, so Hubble's on board, lots of ground-based observatories on board. Obviously, you've just got to wait for tests and we'll get the lovely pre-data as well.
Yeah.
So that was really exciting. And so what they were able to do, I think, from that unique sort of setup and that unique ability to see pre-explosion and really watch the brightness change, because TESS takes basically a photograph or an image every 30 minutes.
Right.
So it really is precise. It can give you that data. Every 30 minutes it was looking at this particular supernova or before it went supernova.
Yeah.
So it's a lot of information. Whereas normally you might have a few odd scattered kind of pictures from the Hubble archive or from some survey archive.
Trawling back through the archives. Have we got something pointing in that direction? And this is, well, it turns out, every 30, what do you say, 30 seconds?
30 minutes.
30 minutes.
Yeah.
Every 30 minutes for how long before the thing went boom?
Yeah, well, nearly 2 weeks.
Wow.
Yeah.
Wow. And over what time, what kind of time scale do you see significant change in a star when it's going supernova like this? Is it on the order of minutes, hours, days, weeks, months?
So it's usually a couple of days to reach maximum brightness. And then depending on the supernova, it will be a few days to a few months to watch it decay in brightness and go back to being a normal dim star again.
So there's a lot of really good data here.
Absolutely.
That's cool.
Yeah. So for the first time, because of this very unique data set, they were able to put together not only just kind of a single way of measuring, say, hey, one of the key things we want to find out is the mass of the progenitor. So how big was the star that blew up, basically?
Sure.
And you can do that by kind of using data from the tail of the light curve by saying, okay, well, if it was this bright at this time, it might have been this mass. But it's all modeling and kind of backwards, CSI.
Sure. Forensic. Yeah.
Yeah, evidence. So what was unique here was that they were able to use not just sort of that one piece of data, but actually 4 pieces of data to find out what the masses were.
Like what? What sort of things can you do?
So you've got the light curve itself, which including Tessa's, stunning view of it watching going from 0 to very, very bright object. You've got your evolutionary models, so your theory, which kind of inputting into that. We've got even some Hubble archival images of these galaxies going back to 1997. So there's some interesting stuff there, which tells you basically even sort of 10, 20 years ago, there wasn't a massively big bright star where the supernova went off.
And you can see that level of detail in something. Sure, okay, it's only 60 million light years away? It's only 60 million light. It's still 60 million light years away, Emily. You can see the level of detail with some of this data of, is there a big star there or not?
Well, you would, if it was like a really big blue supergiant or something like that,
okay.
It would stand out.
So you can start ruling things out. Okay?
Yeah.
It's not one of them.
And then the really big one, which was so useful because it was so close, we could measure very precisely, was the measurements of the oxygen in the supernova as it was exploding.
Right. And so you can work that into the models and go, it's probably one of these of this size.
Yeah. So basically you've got 4 pieces of information. You can have 4 different people doing 4 different sums saying, hey, what do you think the mass was of this progenitor? And it turns out they all agreed really well. And we're down to about 13.5 to 15 times the mass of the sun. Wow.
So is that a big star, or is that kind of does that still fall into the same kind of category? Is this roughly sun-sized?
It's bigger than the sun, so we wouldn't call it a solar type star.
Right.
It is getting into the bigger end, but I guess kind of the middle range of the big type stars.
Right.
Once you get over 20 solar masses, then you kind of go into the massive, exciting stars.
But that's not really the point. The point is it was possible to put all of these 4 pieces of data together and say, do they agree? And how precisely can we nail this down? Which is something which would ordinarily be much harder to do if you're working backwards from just seeing the remnants.
Yeah, exactly. So they're calling this kind of the Rosetta Stone for supernova.
Nice.
Because like the Rosetta Stone, you have 3 different pieces of text in 3 different languages, one of which we didn't understand, which was the hieroglyphics in Egyptian.
Yeah, and then you had Greek and something else.
Sumerian or something like that, yeah. So now we've got, again, 4 different ways of calculating the mass, and they all tell us the same story.
Fantastic. So all we have to do in the future, in order to be able to do all of this again, is just make sure that you spot a supernova in the direction that Tess is pointing, and it's all sorted. You're all good.
It'd be great. It'd be great. But what it does mean is that, the next supernova that we don't catch before it goes, we can apply the same precision to, because we know we've got our standard.
Right.
Yeah.
So this has basically given us more confidence in the various techniques that we've got. If we don't have that prior data, whereas before we was like, well, we think it's this. Now we're fairly sure it's this.
Yeah, exactly.
Yeah, okay.
Yeah, so it's really exciting. So, and then the other part, which was pretty amazing, is that this supernova did something which quite a few supernova type 2s do, but we were able to understand it in a lot more detail.
Okay, what's that?
And that is, instead of dropping off sort of quite quickly after its rise, so normally often a type 2 would sort of drop off over the next kind of couple of weeks, and then it would fade into kind of background. But this one stayed really, really bright for 114 days.
That does seem a long time for a supernova, even my limited knowledge. It's normally weeks, isn't it?
Yeah, exactly.
So 114 days is a lot longer than
it's a few
weeks.
months. Yeah. So this is what we call a plateau type. So basically it rose up, got really bright, and then just kind of plateaued and stayed up there for ages. Now, the reason why this happens is actually because of what's happening when the supernova explodes and interacts with the medium that is around it. So if we go back to what is happening to the star, as it's kind of taking its sort of gasping, dying breaths, if you like.
Sure, why not? Let's anthropomorphize a dying star just even more.
Well, they're interesting
really
objects.
Sad now, but yeah.
Yeah, so these very massive stars, there's a lot of gravitational force crushing the core, right? So they've run out of hydrogen in the core that they can fuse to helium. They've even run out of helium that they can fuse. So they're getting pretty desperate by this point, because they've got to hold themselves up against gravity. Otherwise, we know what happens. It goes kaboom.
And no one wants that.
So as you get hotter and hotter in the core, and you get more and more pressure from the outer layers sort of pushing down, then you go through these stages of fusion. And so you go through, basically you start spinning through the periodic table. It's almost like the star is throwing up, well, hey, I can fuse this for a while to hold myself up.
What about some aluminium? Would you like some aluminium? Will that help? Okay, no. What about iron? Could we do iron?
Yeah. So what happens is, and the higher or the bigger the elements are, the less time it takes to fuse and the less energy you get out of them. So, for example, you can start to fuse carbon. You can do that for a while, maybe 600 years. You can carry on fusing carbon. But then you can go to neon. You only got about a year if you're fusing neon.
You're getting desperate at this point.
If you go to oxygen, you've only got about 6 months. And then down to silicon, you've only got about a day of silicon fusion before you run out.
Wow. So things are really accelerating.
Yeah.
Yeah.
And all through this time, this is all happening on the inside of the star. But there is, of course, a lot of instabilities that mean that the outer parts of the star start to be shed off in what we call a stellar wind. So imagine the very outermost layers of the star just kind of get puffed off. If there's a sort of a mini kind of destabilization, then you get a sort of a larger puff off material.
Because these stars have really expanded by this point, haven't they?
They're
enormous.
So
the sort of, I think we talked about this a while ago, the outer layers of the star, the outer sort of regions of the star, it's becoming quite nebulous at that point. The distinguishing line between star and not star, like that's a very grey area at that point. And so you're just losing bits of it.
Yeah.
Right.
And you've got these instabilities, eruptions, flares. It's all getting quite, dramatic.
Sounds fun.
So lots of the star is actually pushing out into this, what we call the circumstellar medium, so the space around the star. And it's this circumstellar medium that when the star does explode, it sends out a shockwave through. And this is what gets kind of ignited in a sense and brightens up and gives us part of the huge brightness increase of the supernova.
Right. And so you were saying that on this particular one, that became a plateau over months of the region around this star lighting up, right? And my mental image is almost it's catching fire, in a sense, because my mental image of a supernova is boom, right, and it's over like that. There's just this massive explosion, but of course, you've got an enormous amount of stuff being shed, huge amounts of energy ripping through it. So yeah, okay, maybe the physics of the actual collapse, explosion, boom part is over reasonably quickly, but then you've got this incredibly energetic, large and expanding environment, which is going to be really bright.
Yeah,
It's on fire now. Yeah.
So this shockwave, it's moving at something like 1% the speed of light.
Wow.
So, and it's incredibly powerful. So when it slams into that circumstellar material, huge energy dumps into that material, which then ionizes all the species which are there. So yeah, it's not quite on fire, but
it's a good mental image. That's my
well,
mental image.
we're kind of a victim of our own success here because we talk about nuclear fusion as being burning, and that's always been a problem.
But I mean, I'm also, what also falls into my mind is things like, big bomb explosions, and much as I hate to raise the analogy, the classic images of a nuclear bomb going off, an atomic bomb going off, where the explosion itself takes a fraction of a second for that nuclear reaction to go boom. But then you've got this massive fireball rising up into the atmosphere, which is incredibly bright and billowing away and burning and so on. And so there's an analogy there of, the initial reaction like that, but it then carries on its effect for quite a long time in the region around it. So,
yeah, exactly. Yeah. So long as we agree it's just not actually on fire.
No. I'm backing away from that particular bit of wording.
We expect this to happen with these kind of stars. As we say, like even Betelgeuse, it's getting to that point where it's casting off lots of its outer atmosphere. Probably in a typical star, we're expecting something like a third of the mass of the Earth to be shed every year.
That doesn't, for a really, really big star, that doesn't sound like terribly much. But maybe I'm just getting jaded by astronomical numbers.
Yeah, well, it's not. I mean, it is and it isn't. I mean, the Earth is quite big.
Sure.
3 years, you've just shed off the Earth from the sun.
Yeah.
But I guess when you're talking about this happens over hundreds of years, not necessarily kind of just 1 year.
Sure.
So it does add up to quite
a lot. It adds up to a lot.
Mass.
Yeah.
But however, so if you backtrack and then look at, the fact that this shockwave is plowing through all this material means, and it's staying bright, means that there's a lot more material there than you'd normally expect.
Yeah, and if it's staying bright for weeks, months, there's a lot of stuff there.
Exactly. So the back calculation of that says instead of maybe a third of the Earth's mass in a year, we're probably talking about in the year leading up to the supernova, at least, probably something like 200 times the mass of the Earth per day was being shed off this star.
Now we're talking numbers that sound fairly impressive. So what's going on there? I mean, is this just a particularly big and wobbly star? Like, what's going on?
Well, it's incredible, isn't it? You think that there's just this extraordinary amount of material being dumped into the circumstellar medium. The hypothesis is that there was some kind of slightly odd fusion processes going on, something to do with oxygen fusion that meant that the star was a lot more unstable than perhaps it could have been. So it almost had this kind of mini explosion before it went supernova, where it was actually almost like a nova. We talk about nova. I don't know if we have talked about nova a lot.
I don't know. We have put it on the board. I don't think we have talked about novas. Supernova, but a supernova implies a nova. So we should talk about that.
No, we do have novas, and these are kind of stars that get material on the outside. They get a bit unstable, and they kind of sort of have a little explosion and puff it off.
Right.
In a kind of a similar way, then you can have kind of an extra bit of the star's atmosphere dumped out into the circumstellar medium, which is incredible because it tells us something about the last sort of year of this star's life that we would have never known about.
Yeah.
Because it's not something we can see with our own observations.
That's extraordinary coincidence that the one that we happen to get a really, really good look at for a whole bunch of reasons happens to also be a really interesting supernova. That's so cool.
I mean, it's not super rare, and I think that reasonable number of these type 2 supernovas show this plateau, which actually then draws us back to, hey, it turns out these stars, when they're going through the last kind of throes of their life, do all sorts of weird and wonderful kind of things, not just kind of a very simple, slow puff off of material, but they have these kind of very dramatic extensions of that. So I think it's really exciting that something that we weren't able to pick up before, we've picked up because we just happened to be looking at it. And then from the looking at it after the explosion, we're able to then again go back to its early days and even its first, even the whole year before it exploded and find out what was going on.
Right, well, that brings us to the end of a supernova-tacular episode of the Syzygy podcast. Emily, I've really enjoyed this one because not only does it involve everyone's favourite space telescope, no, I'm not talking about Hubble, I'm talking about TESS, of course, and Hubble, second favourite, but, like, what an extraordinary blummin' coincidence it is to be able to get all of that data about this one supernova and then for it to be a really interesting supernova anyway. Like, it could have just been a bog stand, oh yeah, we've seen loads of those. But this one was, guess what? Get ready to learn a lot about supernovas, folks. We've got all of this amazing data. This is so cool. What are the odds?
Very cool. Well, yeah, I think this is just validating the fact that we need to be prepared. Get ready. You know, the next exciting thing is just around the corner.
Well, let's hope not exactly just around the corner, because by the time we find out, it's too late. We're all going to be dead. So not literally, figuratively just around the corner, far enough away for it to be really interesting without being deadly.
And Betelgeuse is probably not going to explode, so it's fine.
Yeah, well, we'll be fine. We'll be totally fine. Listen, Emily, if people wanted to get in touch with us with their favourite supernova-related facts or questions, how might they do that?
Well, you might need to shorten the number of characters first, but you can grab us on Twitter.
Well, actually, if they wanted to, they could just convert everything to base 26 and just do it in supernova math.
Oh, don't do that.
Tell you what, if someone gets in touch with us and puts their message into supernova math, I will do the decoding, because that's just too cool. Might take a while, but I'll do it. There's a challenge for you out there, listeners. But if they were going to do that, how would they do that, Emily?
They would need to tweet it at SyzygyPod, SYZYGYPOD.
That's right. That's how they do that. But they could also get in touch with us on the Facebooks, because we're on the Facebooks. However you find people on Facebook, I think it's just you go and you search for them. You type in the little search box and say, Syzygy Podcast, give me some of that. And you'll find us on Facebook. We're on the Instagram too.
Absolutely.
Yep.
Yep.
With the at SyzygyPod on there. And you could, send us a little message through that one too.
And some of the cool images that we pull into the podcast end up on the Instagram, which was
right.
fun.
That's right. We're all over the socials. Or you can just do old school and go to our website, syzygy.fm, where you can find all of the episodes, all of the show notes, all of the really cool pictures, all of everything, including a contact form where you can send us a little message. Like someone who contacted us recently and said, hey, Emily, Chris, you need to get your act together and start pronouncing things in the same way. I say data. Emily says data or data sometimes. Who knows?
Data.
Is that a New Zealand thing? Is it definitely data in New Zealand?
It's just the correct pronunciation, Chris.
It's just not. But anyway, data. Let's call the whole thing off. Listen, if you wanted to support the show, a bunch of different ways that you could do that. Just tell everyone you know. Tell that space nerd in your life you should listen to this thing, because it's really, really cool. And that'll help us to get loads and loads of listeners and help us to move up through the noise of the podcasting universe. The other thing you can do is give us a star rating on your podcast catcher of choice. That helps other people to find us. And the last thing is, if you want to become a financial member of the show, you can go over to patreon.com/SyzygyPod, where you can throw a couple of dollars, a couple of quid our way every month to help us keep the electrons flowing through the website and to help us do the thing that we do when we're able to do live shows. Every once in a while, we get to go out to a festival or something like that and do a live version of Syzygy. We haven't done that in a while, and I'm really looking forward to the day when we can do that again. Otherwise, I guess that's probably all we've got for this week. I'll see you in about a week. Emily, see you later. Bye, everybody. Well, it's nice to have feedback. Yeah, frankly, I'm pronunciation agnostic. I don't really have an opinion. I mean, I say yogurt now. I can't.
That's wrong.
That was one of the first things that was beaten out of me.
What are you doing?
Pass the yogurt. Beg your pardon.
Oh,
yogurt?
Okay.
Pass the yogurt.
Maybe we can agree on one thing, though.
What?
What is the little machine that sits in your house that broadcasts the Wi-Fi?
That's a router.
Thank you. It is a router.
Had to think about that for a second. No, it's definitely not a router.
No.
Which is in Australia. That's a very different thing.
Yes. No.
Very, very different thing.
No.
Yeah,
I'm
it's
very
definitely
upset
a router
with this country.
Yeah.
About that.
Do they call that here? Do they call it a router here?
Yeah.
Bloody Poms. They don't know what they're doing. In which Emily
Between
and Chris, we should have a new podcast where we just bitch about UK things.
Router and pants, I will never get used to.
Oh, pants. Well, I mean, but I think they did have that one first, to be fair. I think the rest of the world took that and ran with it in different directions. And yeah. But I mean, we do have underpants, which I think is like that clarifies things well.
Yes,
and so I think
does,
if you're going to go, if there's ambiguity, then you go with pants are things that you wear on your legs, and underpants are the things you go underneath those.
Indeed.
And we're there.
No, but the Brits just call them.
Pants. Yeah. Mind you, it does make for a very good swear word. I really do like pants.
I like pants.
And that only works if they're underpants. Like you can't say trousers. That's not a swear word.
Well, I don't know. The British also use crumbs as a swear word, so, you know.
Well, there is that. Right, we're completely off track here. Although I think I've just found the bit that's going at the end of today's episode.